Yeah, so we're going to talk today about how we use Kubernetes within Octopus Cloud. So here's a quick agenda. We're going to talk about what Octopus Cloud is, how we've got Octopus Deploy running as a containerized application, some of the external dependencies that we use for Octopus Deploy, and then we'll go into how we manage our Kubernetes clusters, how we deploy Octopus Cloud, and then we'll talk a little bit about how we scale our cloud instances and some of the future plans that we have on our roadmap. So who are we? We're Pavel and Carrie. So Pavel's a principal software engineer. He's been here since 2016, and he's responsible for a lot of the architecture behind the cloud platform that we have here at Octopus. And myself, I've been on the cloud platform team for the last couple of years, helping engineer some of the infrastructure. But we'll start with a quick disclaimer. So today we're going to talk about some specifics of how we use Kubernetes in the Octopus Cloud. This isn't going to be a tutorial for how you should use Kubernetes or a generic recipe for your own applications, but it might be some inspiration for you if you're looking to go on that journey of moving towards using Kubernetes in your infrastructure. So Octopus Deploy, I'm sure you're all familiar with it, but it's a tool for automating deployments of software and making sure that those deployments are repeatable. And so we offer it, as John mentioned earlier, we offer it both as a self-hosted solution and as Octopus Cloud, where we host it on your behalf. So one of the terms that we use here is a cloud instance. So this is referring to a single instance of Octopus Deploy hosted within the Octopus Cloud. And the beauty of having an Octopus Cloud instance is that as a customer, you don't need to worry about the infrastructure that it runs on. You don't need to worry about keeping Octopus Deploy up to date, and you can focus on your deployments. So if you're interested in starting an Octopus Cloud free trial, you can do so at octopus.com. So for the architecture of Octopus Cloud, we have some guiding principles. And Pavel's written a great blog post about this. We'll have a link to that at the end. But we want to avoid any single points of failure within the Octopus Cloud infrastructure. We expect any cloud resources to have spotty availability from time to time as networks fail and things like that. So we don't want to have any one key point of infrastructure preventing people from getting to their instances. So our Octopus Cloud infrastructure is designed to degrade gracefully or to work around any failure that we see. We also try to design for gradual rollout. So we don't want to do any big bang releases because those are an opportunity for things to go horribly wrong and for the entire system to go down. So whenever we're doing significant changes to the infrastructure or rolling out significant upgrades, we'll do those piece by piece, and we'll do a few pieces of infrastructure at a time to make sure that we're happy and confident that that rollout is going smoothly before we continue it to the full platform. We also try to make all of our infrastructure scalable by default. We know that there's always going to be more load, and we know that it's probably going to show up in places that we didn't expect it to. So we try to avoid any designs that would involve a piece that can't be scaled, because that means that we don't have the knobs that we need to be able to add more load in future and to be able to scale up to handle it. We also try to avoid temporal coupling. So we often have other third-party APIs and things that we call out to, and we don't want to have our software blocking waiting on a response from those third-party APIs. So wherever we can, we'll send those API requests out, but we'll carry on doing other work, and then we'll check in afterwards to see if that request completed. We don't want to have everything go down just because a third-party API became temporarily unreachable. And the other thing is that we try to use officially supported APIs only. So we don't want to be handcrafting our own clients to call APIs. We don't want to be using any special APIs within Octopus deploy that other customers can't see. We want to be making sure that we're following the same process that anyone else would, because these are well-trodden paths. Other people have been there before. They're well tested, and we're not doing anything special. So one of the interesting things, of course, is the fact that Octopus Deploy did not start out as a cloud-native application. So Octopus Deploy was originally only available as self-hosted. And so over time, we've had to develop it and add new functionality to support being able to host it in the cloud. And one of the first steps to do that was to get it running in a container. Although it's possible to run Windows containers, we made the decision to go ahead and make sure that Octopus Deploy could run on Linux by porting it to .NET Core. This gave us a bunch of extra capability and meant that we weren't doing anything particularly special. Windows containers are somewhat special. They're not widely supported. And so, yeah, this removed a bunch of problems for us. But that initial migration from .NET Framework to .NET Core and from Windows to Linux was a little bit tricky, because there were some assumptions that had already been made in the code, common assumptions, things like assuming that the file system is case insensitive, because on Windows, the case doesn't matter, but on Linux, it does. And we also found that .NET Core was fairly new at the time. So when we started doing this, we found a few platform-specific bugs in .NET Core that didn't exist in the .NET Framework. But once we had it running in .NET Core and running on Linux, we could then create a container out of it. Now, you might think that that's fairly easy. You can just go into the Visual Studio menu and just go add Docker support to your project, and straight away you've got a Docker image that you can run. But there are some other considerations that we needed to think about to make sure that it was a good container image that we could manage. So there's a bunch of different configuration that goes into Octopus Deploy, and part of making it available as a container is ensuring that those configuration settings are able to be defined at the time that you start the container. So this is things like the database connection string, being able to point the container at the database, being able to specify the credentials for the first user account. So we don't want to just have an interactive flow for setting up the first user. We want to make sure that we can spin up a container that already has a first user in there. And we also want to populate things like the license key and some of those application-specific details, so that that container can immediately start taking requests as soon as it's running. Now, if you've ever installed the self-hosted version of Octopus, you would be familiar with Octopus Manager. So Octopus Manager is the tool for performing this configuration in a self-hosted environment. One of the cool things about how we've implemented things in Octopus Cloud is that the same APIs that are being used by Octopus Manager, the same command line settings and the same environment variables that are set by Octopus Manager, are the same ones that we use in Octopus Cloud. Another part of moving to hosting our software in a container involved some of the other factors that just make life easier. So we needed to make sure that the application didn't rely on any special permissions. So by default, containers run in a restricted namespace, and they can't perform the same actions that the likes of a Windows application can. So yeah, we needed to make sure that the application wasn't relying on having like admin privileges, those sorts of things. We also had to make sure that the application logged to the console, because a lot of environments, such as Kubernetes, where you deploy containers, they will have separate tools for shipping those logs out and being able to search those logs, and they expect that the logs will be written to standard out from those containers. It's also important to think about any assumptions that you might have about networking behavior. So in the case of Octopus Server, it connects to SQL Server for its database. And in a self-hosted environment, that SQL Server would be running on localhost. So you can't just assume when you move to containers that you can connect to localhost and there'll be a database there. So it's important to think about the fact that in the case of a container, localhost is just your container, and it doesn't contain any of the other services. So you need to make sure that you've got ways that you can point that container at other resources on the network. And the other thing to bear in mind is to try to work with the tooling rather than against it. So often there are sort of patterns that people have implemented when they've moved their .NET Core application to a contained application and those sorts of things. And there are often good reasons why they're doing things the way they are. So it's good to spend the time to understand the reasoning behind those patterns. So in terms of Octopus Deploy, there's a few resources that Octopus Deploy is dependent on that exist outside of that container. The most obvious one, of course, is the SQL Server database. So this is where we store information about the different spaces, the projects, the tenants, and the deployment processes. We also have a dependency on file storage. So if you use the inbuilt package repository to store your releases, they are stored on file storage. We also archive log files there and store some diagnostic data in file storage. We also want to ship those logs from Octopus Server to a logging and monitoring platform so that we can see any errors that pop up and be able to report on how things are performing. And then we've got authentication and authorization providers as well. So within your Octopus Cloud instance, you can configure Octopus Server to log in with Entra ID or Octopus ID or Google, those sorts of things. So those are all dependencies that exist outside of the Octopus Deploy container itself. So we deploy Octopus Cloud in Azure, and so we use a lot of the Azure resources to provide this functionality. So we use Azure SQL DB for our SQL Server databases. We use Azure File Share for the file storage. We use a couple of third-party tools, Sumo Logic and Seek, for logging and observability. And yeah, we've got the various authentication and authorization providers hooked up there. So what do we need to deploy when we're deploying each Octopus Cloud instance? So first and foremost, we spin up a new Kubernetes namespace that is unique to that instance, and that holds all of the components used by that instance. Within that namespace, we create an Octopus container, and that Octopus container also has ingress rules that allow inbound traffic for both the web interface and polling tentacles, which work on a different to the web interface. We also configure volume mounts for the file storage, resource limits for the CPU and memory, and we configure liveness and startup probes. So these are typically just a web request that hits the health check endpoint of Octopus Server, and this allows Kubernetes to periodically check to make sure that that container is in a healthy state. With the startup probe, we have a longer delay on that one, and that's because startup can take a little bit longer if we're applying some database migrations. So if we're in the process of upgrading the version of Octopus Server, then that first startup will be changing the database schema around, and that can take a little bit longer than the normal liveness probes would. So one of the concepts that we have within Octopus Cloud is what we call a reef. And you can think of reefs just as being a logical grouping of cloud instances. Reefs are represented in Azure by a resource group, and that resource group hosts all of the dependencies that are needed by that group of cloud instances. So within that resource group, we have our Kubernetes clusters, we have our SQL servers, and we have our storage accounts. Each reef is hosted in a specific Azure region, and we can't move the reef. So we can create other reefs, but we won't move the reef itself. Within each Azure region, we have multiple reefs, so we can move customers between reefs within that region, or we can even move customers between reefs across region if we need to. So that can happen sometimes if a customer has moved their head office from the US to Europe. They might request that we move their cloud instance closer to them. So this is one way to visualize it. So the blue boxes here are representing the Azure regions. So here we have 3 different Azure regions: West US 2, West EU, and East Australia. And then within each of these blue boxes, we have one or more reefs. There's usually at least two reefs in a region, but there can be more. And then within the reef, we have the SQL servers, the storage accounts, and the Kubernetes services. So networking, how do we communicate between the different resources that we have in Azure? So we've set up a number of private virtual networks in each reef, and only the resources that need to communicate with each other have virtual endpoints within that virtual network. So cloud instances within a reef can talk to SQL servers and storage accounts within that reef, but they can't. They don't have any network access to resources in other reefs. And then Cloud Portal, which is what we call our management plane, it has access to all of the resources because it has endpoints on each of those private networks. When we're deploying our Kubernetes clusters, we use the Azure Kubernetes Service, AKS, to deploy and manage the clusters and the nodes. This is because we don't really want to be looking after individual virtual machines and their health. So we'd much rather use a managed service to provide that for us. We currently deploy those clusters in 3 different regions, the US, Australia, and Europe. And then each reef will contain multiple Kubernetes clusters. This allows us to move customers around within the reef and also makes it easier for us to perform upgrades of those clusters. We also make sure that customers' data is kept within their chosen region. So when you go through and set up your instance, you get to choose a region. And we stick with that for 2 reasons. The first is to ensure that we keep latency to a low limit, and also to ensure that we meet any data sovereignty requirements with things like GDPR and those sorts of things. So in terms of cluster security, what are the things we do to improve the security of the clusters? Well, one of the things is to ensure that the cloud instance runs in its own namespace. So we want to reduce the risk of someone breaking out of their own cloud instance and trying to attack other instances. Because they're in their own namespace, if they break out of their own cloud instance, they'll find that there's nothing else there that they have access to. We also ensure that the cluster management APIs are only accessible from private VNets. So by default, when you spin up an AKS instance, those management APIs will be accessible on the public network, the public internet, so that you can access them from wherever in the world you are. But we only ever need to manage those clusters from tools like Cloud Portal, and so all of those tools exist within our Azure private networks. Within Azure, we've configured role-based access control, so we know what each account needs to be able to do, and each account is limited to only those things that it needs to do. We don't have any sort of global super admin accounts. We just want to have accounts that are scoped to exactly what they need. And where possible, the authentication between Azure resources is performed using Azure managed identities. So these are user accounts that Azure manage and create. And every Azure resource can have a managed identity. And so in cases like this, we can configure it so that Cloud Portal, for instance, has its own account that it will use for interacting with the Azure APIs. And so we can define ahead of time with role-based access control the different APIs that Cloud Portal needs to be able to call, and it can't call any other APIs because it doesn't have permission to do that. So Kubernetes upgrades, how do we go about rolling out new versions of Kubernetes? So each Kubernetes cluster that we have, we consider it to be ephemeral. We can blow it away at any time and create a new one, and we won't have lost any customer data in doing that. We use what's known as a blue-green deployment process to upgrade those core Kubernetes components. And this involves us creating brand new empty Kubernetes clusters. We then deploy our dependencies and ensure that test workloads are running well on that new cluster. And then once we're confident that the new cluster is performing correctly, we then start moving customer instances across one by one when they reach their maintenance window. And in doing things this way, taking a slow approach upgrading between clusters. We've got a few compatibility issues. So one of the recent ones that we found was a change in file locking behavior in AKS for our Azure file shares. So it was important that we caught that one so that we could make some changes to the product to work correctly with the new file locking behavior. So how does that look in practice? So here we have an existing cluster running Kubernetes 1.29, and it has 3 different instances on it. So these are 3 different pods, basically. Now we want to upgrade that Kubernetes cluster to 1.30. So the first thing we'll do is we'll create a brand new cluster. So we've got our blue cluster, and we now have our green cluster. You'll note that there's nothing running on that 1.30 cluster yet. That's because we've just spun it up, and we're going to go through and test it and make sure it behaves correctly. And then we're going to move our first instance across, and this is probably going to be one of our test instances. So we'll spin that instance up, we'll use the web interface and use testing to interact with that and make sure that it's behaving itself and that everything is performing correctly. And then we can start migrating other instances across one by one when they reach their maintenance window. So an hour or 2 later, instance 2 hits its maintenance window, and so we can shut down the pod on the 1.29 cluster and spin up a new pod for that instance on the 1.30 cluster. And then eventually, after about 24 hours, we'll probably have all of the instances moved across to that new cluster, and that old cluster, the 1.29 cluster, doesn't have anything running on it anymore. And so at that point, we can blow it away, and we're left with our new cluster running the new version of Kubernetes. So this is a nice approach for us because it means that at any point in the process, we can stop what we're doing, we can roll back, we can easily have different clusters in different versions where we need to when we're doing bigger upgrades. So it gives us a lot of flexibility with those things. So alternative paths. Why don't we just have one big Kubernetes cluster, a global cluster? So this is all in line with our principles, right? We want to be able to easily scale our infrastructure. We want to be able to do gradual rollouts of those infrastructure changes. We want to be able to reduce the blast radius of any incident. So in the case that something goes wrong with that first instance that we've moved across to that new cluster, we only want that instance to be impacted. We don't want all the other instances impacted at the same time. The other catch with having a large Kubernetes cluster is that it would be dependent on core Azure services in a specific region. Because each cluster can only exist in a specific region, it would be dependent on services in that region, and therefore there'd sort of be a single point of failure there. That entire region would have to be online all the time for the cluster to be reachable all the time. And this approach that we have with multiple reefs and multiple clusters also makes it really easier for us to spin up development and test environments because they can be deployed in the same way as our production environment. So there's nothing special about our production environment. It's not like it's a special production cluster. It's a cluster just like any other development or testing cluster. It's just a bit more locked down because it's production. So we've recently adopted a new feature of Octopus Deploy called the Octopus Kubernetes Agent. And this is a way that we can directly connect our clusters to Octopus Deploy. So this works really great for us because it means that the cluster itself is connecting to Octopus Deploy rather than Octopus Deploy reaching into the cluster. And so this means that we can tighten the security around our clusters. And our dynamic workers don't need to have permission to access the Kubernetes clusters because the clusters will reach out to Octopus Deploy itself. It also means that a bunch of the different deployment steps that we have within our deployment process can now be run directly as script pods on the cluster. So this avoids the need for us to use dynamic workers in a lot of cases. And so that's just another thing that speeds up the development process, the deployment process, and means that we can reuse some of that existing infrastructure for performing tasks. It also means that a lot of those things perform quicker for us because they're running directly on the cluster that they're making changes to. So pretty much every request is happening on that same node. So I'm sure you're unsurprised to find that we use Octopus deploy to deploy Octopus deploy. So we try to drink our own champagne. So we have Octopus Cloud instances that we spin up called hubs, and each hub manages the instances within an Octopus Cloud reef. We coordinate those hubs using our internal tool known as Cloud Portal. And so Cloud Portal will start deployment on those hubs when a customer's instance is due for an upgrade and within their maintenance window. And those hubs will go through the process of shutting down the customer's instance, ensuring that all the required components are upgraded, and then it will push out a brand new deployment to the appropriate Kubernetes cluster and wait for that deployment to come online. So Cloud Portal, we've mentioned it a few times. What is Cloud Portal? How do we manage all the infrastructure that we've got? So Cloud Portal is a custom .NET web application that we've written that ties everything together. So it runs various tasks, and each task implements what's known as the saga pattern. So this is a way for us to have long-running tasks, and each time the task performs an action, it will store its current state in the database. This means that at any time we can redeploy Cloud Portal, and it will pick up exactly where it left off from by reading the existing running tasks out of the database and resuming with the next step in that task. So Cloud Portal is responsible for lots of things within Octopus Cloud. It creates the cloud infrastructure. So when we want to create brand new reefs or we want to spin up brand new cloud instances, Cloud Portal will do that. It's also responsible for scaling and upgrading cloud instances. So it will monitor a cloud instance and see that it needs more resource, and therefore put in a request that it gets scaled up during its next maintenance window. Or that a cloud instance is running an older version of Octopus Deploy, so there will be a task set up to upgrade that cloud instance in its next maintenance window. We also use Cloud Portal for coordinating the Kubernetes cluster upgrades itself. So we can schedule those within Cloud Portal, and it will go through the steps of that we talked about earlier, the blue-green deployment. It will spin up the new cluster and slowly start moving instances across at the appropriate times. All of the tasks that happen for cloud instances happen within the maintenance window. So Cloud Portal is responsible for managing those maintenance windows and ensuring that we get as much stuff done within a maintenance window as we can. It also collects and collates some performance and availability metrics across the platform. So a lot of the resources that we use can report metrics directly into Sumo Logic, which is our metric tool that we use. But there are some other metrics that only Cloud Portal has access to, particularly things around maintenance windows, because those are a Cloud Portal specific concept. And Cloud Portal can also alert a member of the Cloud Platform team when there's something that comes up that needs our attention. And so this is a quick little screenshot of what Cloud Portal looks like in our staging environment. So this is the dashboard showing us a bunch of different metrics within the platform and showing each of the cloud instances and how they are performing in regards to that metric. So maintenance windows, I've mentioned those a few times. What are the different things that happen within a maintenance window within Octopus Cloud? So any number of these tasks can be performed, including 0. So not every maintenance window is used. We don't necessarily need to take your instance down every day, but when we need to, we will use that maintenance window to upgrade your instance to the latest release of Octopus Cloud. We also use it to make changes to the memory and CPU limits of the cloud instance. And this is because we need to restart the cloud instance for those changes to take effect. We also go through and do maintenance tasks like rebuilding database indexes and compacting the database. One of the other things that we can have is we can have cloud instances that have been quite quiet, and now that customer is doing a larger deployment and all of a sudden they need more resources. So we can move cloud instances between reefs to ensure that all of the cloud instances have all the resources that they need. And of course, we use the maintenance window for performing infrastructure upgrades. So even though the cloud instance itself might not change, we might need to change the platform underlying the cloud instance. Things like Kubernetes upgrades require us to shut down those cloud instances and spin them up on the new cluster. So scaling our cloud instances, how do we manage scaling within Octopus Cloud? So for external resources, these can be scaled independently. So things like the Azure SQL Server database, we can go into Azure and ask them to increase the number of DTUs available for that customer database if it's starting to get busy. And we can also perform vertical scaling of our cloud instances. So we can increase or decrease the CPU and memory requests and limits for that instance. We can move customer instances to other clusters when the cluster that it's on is nearly full. And we can create brand new clusters with larger VMs for each node if all of the existing clusters are full. One thing we can't do yet is that we can't yet horizontally scale a customer's instance. But that's something that we're working on. So what does that look like? So in the case of vertical scaling, we're just taking the existing pod and making that pod bigger, giving it more resources. So in this case, we've got a pod that's running 1 gigabyte of RAM and 1 CPU, and we can vertically scale it up to have 1.5 gigs of RAM and 2 CPUs. In the case of horizontal scaling, which is what we want to be able to do, we end up just spinning up more pods. So those pods aren't any bigger, we just have more pods, and any of those pods can perform the operations within that cloud instance. So this is where we come onto our future plans. How would we like to be deploying Octopus Cloud in the future? So one of the things that the team are working on is trying to support multiple pods per instance so that we can do horizontal scaling. This would also provide some redundancy so that individual pods can be stopped and replaced. And this would mean that when we're doing things like Kubernetes upgrades, customers wouldn't notice any outage because it would only be individual pods within their instance that would be being moved at a time. So as I mentioned, that this is not yet supported. The work's ongoing. There's a lot of work that needs to happen behind the scenes to make sure that we don't end up doing things like running multiple deployments at multiple times from different pods. So we need to make sure that all of the pods for that instance have the same view of the world, and only one of them takes the action of starting a deployment. We want to make sure that those deployments recover safely when that pod is replaced. So if one pod goes down because we're moving it to another cluster, we don't want Octopus Server to forget about the deployment that it just started. And we also want to make sure that any users of that cloud instance see the same view of the world. So we wouldn't want a scenario where one customer is talking with one pod and they see that version 1 has been deployed of their application, but another customer that's hitting the second pod of their instance sees that there's a different version deployed. So there's a lot of work to make sure that each of those pods has the same consistent view of the world, and that only one action is happening at a time for things like deployments where we can't safely run a deployment multiple times. And if you're interested in any of these things, you can follow the progress on our roadmap at roadmap.octopus.com. So useful links. So here are a bunch of the things that we talked about today, if you want to go and read more about them. So early on, we had Pavel's overview of the architecture of Octopus Cloud, and we're going through some of the guiding principles for that. Pavel has a blog post where he goes into a lot more detail about the reasoning behind those principles and how we implement them. We also mentioned the Octopus Kubernetes agent. So this is a reasonably new piece of Octopus that we're using to run part of the deployment process directly on the Kubernetes cluster. There's also links here for what's a blue-green deployment if you want to find out more, and the saga pattern that we use for tasks within Cloud Portal. And last but not least, our cloud platform team is currently looking for a senior software engineer. So if any of this appeals to you and you're a senior engineer and you'd like to come and work for us, you can check out that job posting at octopus.com/company/careers and have a read up and put your application in. So thanks, everyone. I hope that was helpful.